Oh, hey guys. Welcome to your Chapter 2, Lesson 8, Notes on Proportions and Similar Figures. By the end of the day, you will be able to find missing lengths and similar figures, not fingers, and to use similar figures when measuring indirectly, because sometimes you can't always measure exactly what you want, but you can figure it out. So, let's get started right away. I said we'll be talking about similar figures, and when I say a similar figure, they always come in at least pairs because you need something to be similar to. So similar figures have the same shape, but they don't necessarily have the same size. We'll talk about lots of examples. And when you look at this word similar, similar comes from the same root as same, also synonym, which means same meaning. When you're similar, you have some same thing in common. You have something in common. For example, some of my friends and I are similar because we all are pretty athletic people. We have our athleticism in common. One of my friends loves basketball, and I'm absolutely terrible about it, but we both like to be active. Okay? So similar figures are figures that are similar shapes. They have the same shape. Okay? So our key idea of the day, what we'll be doing today, is we will be using proportions, what we know and love, proportions to find missing side lengths in similar figures. We're also going to use proportions to measure real world distances when we can't measure them directly. So here I have two similar figures for you, and these are similar because they are the same shape, not because they are both triangles, that's a first necessary step, but because they have the same proportions of their side lengths, because as you'll find out in geometry, similar triangles have the same angle measures. Okay? I should have included this in the instructions, but when you see this, you'll notice that, let me get some color coding going on, sorry. You'll notice that A lines up with X, and that B lines up with Y, and that C lines up with Z, as in Z or zebra. They don't always have to be oriented the same. I could rotate this around or flip it upside down or whatever, but they'll still line up. And because of this, we'll write it like this. Because, actually let's go with blue, because similar figures. So we say that triangle ABC is similar to this squiggly guy right here. This means similar to, so it's not exactly equal, but similar to triangle X, Y, Z. Again, notice the corresponding parts. C matches up with Z, as in Zulu, and B as in Bravo matches up with Y as in Yankee, and A as in Alpha matches up with X as in X-ray. Because of this, we can set up proportions. So we know that this length, man, I'm going to need all kinds of colors here today. This length of AB is going to have this, so AB to XY is going to have the same ratio, so AB to XY is going to have the same ratio as BC to YZ. Is BC to YZ. And that'll have the same ratio as, oh, purple, nice, as AC to YZ. XC, I mean, ooh, as AC to XZ. So it's very important that the corresponding parts line up, and notice that wherever we have an A, we have an X that goes with it, and wherever we have a B, we have a Y that goes with it, and wherever we have a C, we have a Z that goes with it. They always line up. But this is our key idea right here. We're going to set up proportions to find missing lengths. So let's look at this guy right here. In this diagram, they tell us that ABC is similar to triangle DEF. So what is the length of DE? Well, when we line these up, we know that A goes with D, so I'm going to match them up, and that B goes with E, so I'm going to match them up as well. So if I want to find this length here of the segment DE, I need to match that up with segment AB. So I know that whatever AB's length is, that lines up with whatever DE's length is. Isn't that so cool? So cool. But how do we know what that ratio is? We need to find something else that matches. Aha! Well, we know that B and E go together, and we know this length. We know the length of BC. Well, what does C correspond to? C corresponds to F. Ha ha ha! That's going to be very helpful. So since we know that BC, or B goes with E and C goes with F, then BC goes with EF. Nice. So BC is the same ratio as, or BC over EF is the same ratio as AB to DE. So we can, wrong tool, sorry. So because BC matches up with EF, we're going to use that to find out what DE is. So you need to line up the corresponding parts. Okay, what is the length of AB? Well, AB is 10. So I'm going to substitute that in there. What's the length of DE? Well, we don't know. That's the question. How will we call it L for length? Oh, great job. Okay, BC, that's length 16. And then finally, EF, that is length 12. Check out this amazing proportion. So we know that the ratio of AB to DE is going to be the same thing as the ratio of BC to EF. So we set them up equal to each other, and now we solve a proportion. How do we solve a proportion? We need to find our cross products. Absolute love. Okay, so on this side we have 10 times 12, whatever that turns out to be, and on our other side we need to find L times 16. I'm going to do 16 times L because that's 16L. So that's great. 10 times 12 is 120. And we're almost there now. All we need to do is get rid of this 16 guy. So we'll divide by 16, divide by 16. And we did that so that our 16 times L reduces out with our divide by 16. And we're left with L equals 7.5. So the length of DE is 7.5. Is that great? Amazing. Now just to do a quick spot check of our work here, AB to DC, AB is shorter than BC. So if we got a length here shorter than EF, we probably did something right. Cool. So good job, guys. You nailed it. Also, it's a little bit more than half. So half of 16 is 8, and 10's a little bit more than half. So that, okay, cool. Half of 12 is 6, and 7.5 is a little bit more than that. So we are right on target. All right, excellent. Okay, that's cool. But when are we going to use this in real life? Well, I'm so glad you asked. Let's say I need to measure a building, but I can't because my ruler is not that tall. Well, we can measure something that's close. So we know that the sun's rays strike the building and the girl at the same angle, forming two similar triangles shown. What's hidden here is their shadows. So if we have a beautiful little sunshine, if he's at that angle, he'll be like right here, right? Amazing with that sunshine. My mom's an art teacher. Isn't that fantastic? She'll be so embarrassed. Okay, anyway, and so they're casting shadows. So we've got this shadow of this girl right here. Great. And oh, we forgot to do her bow on her shadow, you guys. What a tragedy. Okay, there it is. And then the building is also casting a shadow here from the sunshine. So there you go. So we can measure the girl's shadow is 3 feet long, and the building's shadow is 15 feet long. And we know that this girl is 5 feet long, so 5 feet tall. Sorry. So she's either a tall girl or a short young woman. We'll go with girl, though, because that's fewer syllables. All right, they form similar triangles. So how tall is the building? Well, we need to set up a proportion. Set up a proportion. And then we're going to spell proportion correctly. Set up a proportion. Well, what do we know? We know the shadows, so we'll put the shadows on one side. And we need to find the heights. Well, first of all, what is the girl's shadow? The girl's shadow is 3 feet long. And the building's shadow is, the building's shadow is 15 feet long. So that'll give us 3 over 15. Now you'll also notice that I'm labeling this ratio as girl to building. Why am I labeling that? Well, that's because our proportion, remember, needs to have similar figures in similar spots. So we need to make sure that on our second ratio, we have the girl's height up here on top, and then the building's height on bottom. We know the girl's height is 5 feet, and the building's height is, x feet. They already picked a variable for this. That was so kind. X feet. So, I'm sorry, I did the wrong colors. Hold on. Okay, so the girl's height is 5, so we're going to put that on top in pink. And the building's height is X, so we're going to put that on the bottom in blue. So notice they still correspond. The girl is on top and the building is on bottom. Does it matter what we pick for top and bottom? It does not matter. I could have put the building both on top and the girl both on bottom. As long as they're together, that's what we care about. Okay. Also notice that the shadows are in the same ratio, and the heights are in the same ratio. So they need to go together. Okay. So keeping in mind that all of our measurements are with their buddies, hey guys, we have a proportion. That's so cool. We got 3/15 equals 5 over x. Now to solve this proportion, I'm going to make that bigger so you can see. To solve this proportion, now we need to find cross products. So we'll do 3 times x, which is 3x, equals 15 times 5, which is 75. And now to solve for our x, we just divide by 3, x equals 25. So that tells us that our building is 25 feet tall. Which also tells you that, man, my drawing is very much not to scale, because look at this girl. We claim that she's 5 feet tall, but this building is like 5, 10, 12 feet tall. Yeah, so drawing not to scale. So we set up the proportion, and then we solved it. To solve. And we love it. Okay, brilliant. Okay, so that's helpful for finding indirect measuring. Indirect was we couldn't measure the building directly, so we set up a proportion to find out what its height was. We do this a lot with scale drawings. We can create scale drawings. We can use scale drawings. So a scale drawing, you ready for your bad definition of the lesson? A scale drawing is a drawing that is to scale. Okay. Scale drawings are drawings that are similar to an actual object or a place, like a map. Maps are, any good map is a scale drawing. We call the ratio, so you have similarity, right? The ratio is called the scale, and that's why they're called scale drawings. So we have this beautiful map. There's also a helicopter in the background, so I apologize if you can hear that. We have this map, and you know that the distance between Jacksonville to Orlando on a map is 1.25 inches. What is the actual distance between the two cities? So here's this amazing map that I drew. I traced it. But I put the time in to draw it for you. You're welcome. Okay, and we know this actual distance right here is going to be a scale of 1.25 inches. Orlando is where Disney World is. Jacksonville is where the Jaguars play. Just FYI. Okay. So we learned from our definition up here that the ratio is called the scale. So we're going to set up a ratio that's similar to an actual object based on the map's distance. So the map scale is equal to the map distance over the actual distance. And what do we know? Well, our first step is always to define our variable. So step 1, spell step correctly. We need to define our variable. And what are we trying to find? We're trying to find the actual distance between the two cities. Yay. Okay. So we're going to say let x equal the distance from Jacksonville to Orlando. Oh, you guys, I left out a very key piece of information for you. In the map, we are told that the scale is 1 inch to 110 miles. I'm sitting here trying to figure out how are they going to know this. I forgot to tell you the scale. That's the scale. You're welcome. Okay, that makes things a lot easier. Okay, so if our scale here, it's in the ocean, so we'll make it blue. If our scale 1 inch represents 110 miles, let's plug that into our scale. Okay, so we know that 1 inch equals 110 miles. What else do we know? We know the map distance from Jacksonville to Orlando is 1.25 inches. So that map distance is 1.25 inches. And we are trying to find the actual distance, and we said we're going to make that x. So we'll just call that x miles. Awesome. So what did we just do here? We set up a proportion because we set two ratios equal to each other. So we set up a proportion. Who needs spelling? This is math class. I'm just kidding. Spelling's important. Okay. Proportion. We set up a proportion. Nailed it. Excellent. And then our third and final step is solve our proportion. We solve proportions by using a cross product, or rather by finding the cross product. So we'll do 1 times x. Oh, that's going to be so nice. I love 1 times x. That's literally x. Equals 110 times 1.25. Whatever that turns out to be. So 110 times 1.25, and that is equal to 137.5 miles. Nailed it. There you go. We did it. Yay. Okay. Notice when we set up our proportion that we need to have similar figures lining up. We always have the map stuff together, and we have the real distances together. We have our scale all together, right? 1 inch represents 110 miles. So these go together because they represent each other, represent. And then 1.25 inches represents the distance between the two cities. So this ratio is between two cities, is a tale of two cities. Just kidding. That book is about London and Paris. And this represents just a regular scale on the map. And then across the top, we have map distances, and across the bottom, we have real life distances. So those measurements need to line up. They need to be in pairs with their corresponding buddies. Okay, awesome. We have one more left to go. Okay, so that's a scale drawing. A scale drawing is a two-dimensional thing. It's a drawing like a map. Excuse me. You can also have a scale model. Now, a scale model is not a fashion model. It's not someone who's going to put on your scale and carry it down the runway. Rather, a scale model is a 3D model, like a sculpture or a figure that's similar to a three-dimensional object. Like, there's this museum that has a giant model heart. Like, it's this giant thing that's shaped like a heart, and it's this big ol', like, whatever hearts look like, right? But I can't actually draw that. So we're going to use the cute heart instead. So they have this giant model heart that's 14 feet tall. Oof. This is ideal for a person who is 140 feet tall. So if we have our giant heart that's 14 feet tall, that would go inside of a giant person who's 140 feet tall. Wow. Now, what size would we expect the heart of a man who's 6 feet tall to be? Well, we need to set up a proportion, and then we'll solve it. So step 1, set up a proportion. So proportion is when you have two ratios that are equal to each other. And remember, you need to have your buddy measurements lining up. So let's put the heart on top and the overall person on bottom. We'll set up a giant ratio, and then we'll set up a regular sized person ratio. So how tall is the giant's heart? Well, the giant's heart is 14 feet. And how tall is the actual giant? Well, he's 140 feet. Cool. And how tall is a regular person's heart? Well, we don't know. That is the question. What size would we expect his heart to be? Oh, we didn't define our variable. Oh. Let H be size of his heart. Okay, say H for height. Heart. Oh, H for heart. Oh, that's much cuter. And then his height is 6 feet tall. Sweetums. Hey guys, check out the proportion. Now that we have this amazing proportion, let's solve it. So we have 14 over 140 equals H over 6. So we need to cross multiply. We get 14 times 6 equals, on the other side, we get 140 times H. 14 times 6 is 84 equals 140 H. I'm gonna just move this just up here a little bit. Oh, maybe I'm not going to. Okay, there we go. And then to solve for H, we will divide both sides by 140. Divide by 140, and we get that H equals 0.6. Okay, size of heart, remember, in feet. I forgot to specify that. This is in feet. So the heart is 0.6 feet tall. Guys, I don't know how big 0.6 feet tall is, so I'm going to convert that to inches real quick in a second proportion. So you have 0.6 feet over, did we do conversions yet in this class? I'm doing my my lessons all out of order. I know 1 foot is 12 inches. We don't know how many inches are in 0.6 feet yet, but we can cross multiply, giving us x equals 0.6 times 12. 0.6 times 12 is 7.2. So x in inches is 7.2 inches. So that I can do. Yeah, nice. Okay, that's cool. So the heart is 7.2 inches tall, or 0.6 feet tall. There you go. Remember, 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 when you are setting up proportions, they need to align. You need to have your similar figures in the similar spots. Just like up here, you had all the girls' measurements on top, all the buildings' measurements on bottom, and all the shadows in the same ratio, and all the heights in the same ratio. The similar ideas need to be together. And that's how you set up your proportion. Have a fantastic time on your homework. And yeah, we'll see you tomorrow.